All right, so the purpose of our lab today is to study the nature of centripetal motion, meaning circular motion, and trying to find the relationships between the mass of the actual object that we're spinning versus the length of the radius that we're rotating it around us, as basically like it's orbiting the sun or something like that, versus the forces that it's being created, and we're trying to hold up a certain force in the air that's going to be hanging. So we're basically going to be comparing centripetal force to the weight of an object. Me spinning over my head, this little stopper is going to hold up a little mass that's just kind of hanging there in just air. And we're going to be kind of holding up this mass that's hanging in there. Again, any single object that we spin around is going to undergo acceleration because the direction is constantly changing in circular motion. If you have acceleration with a mass, you've got forces. Force equals mass times acceleration, Newton's second law. So the fact that this thing is changing direction automatically creates this force that we call the centripetal force. Again, those are going to be functions of the mass, the radius, as well as your velocity. Basically, here's going to be our contraption for the most part. You guys have this rubber stopper that's going to be attached to a string with a knot. The rubber stopper, again, it's rubber, so it's not like it's metal or anything like that. If it does hit you in the head or you know, whatever, not going to literally like cut into your head. It's rubber, but it's still hard rubber. So again, you want to avoid being hit by the thing, period, especially when we start spinning this thing around pretty quickly. Always make sure that the knot, you know, just kind of keep pulling on that knot every couple times that you do it, just to make sure, you know, it's good and tight. We got a PVC pipe that you're going to be hanging on to. It's good, you know, unless you got like Shaquille O'Neal hands, your hands will fit perfectly around it, holding on to it. We're going to be measuring a distance out. That's going to be our radius here. We're going to be doing two different radii, a 60 centimeter and an 80 centimeter that we're going to need to measure. That's why we have the meter sticks out there. Then we're going to be having a weight. We're going to have anywhere from 100 grams up to 250 grams being suspended from the same string. So basically, we're going to need a force that's pulling up here that's equal to the weight of the object. This pulling force or this tension force is going to be basically then pulled through and coming through basically on the stopper. So the centripetal force up here is going to have to equal this tension force down here, which has to equal the weight. So really, the centripetal force has to equal the weight. And we're just going to want it just balancing in the air. How am I know it's not moving up or down? You're going to put a piece of tape just underneath the opening here, and you're going to pretty much just kind of keep your eye on that tape and make sure the tape doesn't move down or move up. And how will I do that? You'll swing faster or swing slower to try to get that tape in place. All right, that's the whole idea of this. And I'll show you kind of what it's going to look like in a second. So let's kind of look at our different formulas here that we're going to be working with. So we've got our centripetal force formula. That definitely we got going on there. Mass, velocity squared, radius. The mass here is your stopper, because that's the thing that's actually physically being swung around. So M1 is the stopper mass. You guys will go over to the little tiny scales and measure it and figure out how many grams it is. That'll be the first thing you do. How fast is it spinning around? You're not going to be able to figure that out. You're not going to put basically any kind of like little speedometer on there. Right, Matt? So we're basically going to be calculating that. The radius is going to be that 60 to 80 centimeters that you guys measure. And then the centripetal force, we're going to basically find what that is, because again, the centripetal force tension up there has to equal the weight down here. So basically, whatever the weight is, we actually know the centripetal force. So the only thing we don't know is Mr. Tangential speed. The mass is going to be that 100 grams, the 150 grams, the 200 grams that we're going to be putting on there. Those are the weights that are at your table. And obviously, we got gravity 9.8. We're going to then turn that tangential speed into angular speed. We're going to figure out how many revolutions per second this thing's spinning. Okay, how many revolutions per second it's spinning using the radius, which again is that 80 centimeters or 60 centimeters. But again, this cannot be calculated with revolutions. It's got to be calculated with radians. So we're going to do a little bit of a conversion while this is all being said and done. All right. So we're going to kind of piece this all together right now to first figure out that first part. Real quickly, add this on there. The little S hook that you're going to be hooking your weights on, the S hook measures 3.9 grams. So basically, the mass that we're going to be hooking and let it hang from the sky is not going to be just 100 grams. It's going to be 103.9 grams, or 153.9 grams, 203.9 grams, 253.9 grams. So make sure those masses you add the 3.9 on. Otherwise, your numbers will be a little off, and you'll already be off like a percent or two. All right, so make sure we include that. The rubber stopper, you'll go over and measure it. Let's take a look. Let me just, which is actually, mine was 0.029. Do not assume that it is 0.029. Some of the stoppers are just a little bit bigger. Some of them, when I drilled it out, have lost a little bit more mass or a little less mass with the drill bit. So make sure you do measure it. All right, but let's assume that the first one is 0.03, which is really close to 0.029. Make it easier for us. So basically what we're going to do is we're going to set the centripetal force, the spinning force, which is all of this. And we're going to set it equal to the weight of the thing hanging, which is simply that. All right? So this is going to be the mass of the thing that's spinning around. The mass of the thing spinning around is this guy right here, 0.03 kilograms. Now you got to understand, when it was on the actual scale, it was not 0.03 kilograms. It was actually 30 grams. And then I moved the decimal over 1, 2, 3,000. So make sure when you measure it, it's going to give you like 31 grams, 32 grams. Make sure you divide it by 1,000 and get your point, whatever it might be. The velocity, we're looking for that. The radius, the first one is going to be 80 centimeters. Do not plug in 80 centimeters. Make sure you switch that over to meters, which would be 0.8 meters. So we're doing the first one for you right now. And actually, you could use this as your work. Remember, I only need one work. All equal to the mass. Now, this is the thing that's being held up into the sky, being basically just hanging from the string. That 103.9 grams. No grams in my formula, kilograms. So make sure you divide that by 1,000. 1, 2, 3 over. That would be 0.1039 then. Times 9.8. So, oh, and don't forget to square the velocity, right? So we've got my centripetal force. That's the little stopper being swung around. There's the radius that's being swung around at. We're finding the velocity. There's the mass of the thing hanging, and there's gravity, so that's total weight. All right, so do a little bit of number crunching here. 0.03, I can divide that by the 0.8 right now. At least take care of that. So when I divide these two guys, I get 0.0375, v squared. Over there, we got 0.1039 times 9.8. That'll be 1.018. We'll divide by the 0.0375 to get rid of that. Divide by 0.0375. Puts my velocity squared up at 27.2. And then we square root. Square root that value. The tangential speed of that stopper as it flies around is going to be 5.21 meters per second. Again, that's that tangential speed. It's not the circular. It's if I were to let go of it at any point in time, it's going to shoot off at about 11, 12 miles per hour in this scenario, okay, which is kind of slow. But again, we're not trying to hold up much weight. So I don't need to swing it really fast to hold the weight up. Makes sense. All right, omega, radians per second. We showed you guys this formula. Tangential speed is omega radius. Talked about that yesterday. I think we did one little problem with it, or actually 2 days ago. So we got our tangential speed, 5.21, equal to, we're going to find our omega. And again, the radius was that 0.8. So this is pretty easy. Divide by 0.8, right? So 5.21 divided by 0.8 is 6.51. And that would be radians per second, because whenever you calculate or work with omega, it's radians per second, not how many times it spins around a second. So we got radians per second, 6.51. Lastly, I don't know what that means. You know, 2 pi, that's 1/6. I need to know, like, hey, it's spinning around twice every second, 3 times every second. How many revolutions per second? So we're going to do a little conversion here. 1 revolution is 2 pi radian. So here we go. 6.5 radians per second multiply that by our conversion. We want to get rid of the radians, so we're going to put the 2 pi radians on the bottom, and we're going to put the 1 revolution on top. So really, radians cancels radians, and all I'm going to have left are revolutions per second. So how many times this thing's going to spin around? Every 1 second. Once, twice, 2.5 times, I don't know. 6.51 divided by 2 pi is 6.28. 2 times 3.14. So divide by 6.28. It's going to swing around just over 1 time every second. Every time 1 second, 2 seconds, 3 seconds, 4 seconds, most likely. If this works out the way that I think it should. All right. So these calculations, personally I would do these later, because you don't have to do these in class. All right, so this part, I would maybe do one in class as a group to make sure, are we getting this right? So that way when you go home tonight, it's not like you're totally messing it all up. So I would do at least the next one in class, or you can do more, great, but I would do one of these before you leave. All right, but the main thing is we need our experimental data before we go. This you can calculate at home. All right, so just over 1 revolution a second, at least for this one. Question with that? All right, so moving forward, here's basically what it's going to look like. So once you get going here, the first thing you're going to want to do is you're going to want to I put blue pieces of tape around out there. You're going to want to put a piece of blue tape about 1 centimeter or so below, or 1 inch, you choose, don't matter to me, something that you can mark. When the length to the middle of the stopper here, you're going to want one of them to be at 60. Put a piece of blue tape there. Then you're going to want one to be at 80, and you're going to put another piece of blue tape wherever that is, okay, underneath. So you're going to have 2 pieces of blue tape. That way, when you're swinging it around, you can watch that blue tape and see what you're getting. Make sure the 80 and the 60 are from the edge of the little tube to the center of the stopper. I have too many people putting it down like, oh, I'll put the tape 60 centimeters. No, we need the radius of the thing spinning up here to be the 60 and the 80. All right, so if you got any confusion about that when you're setting this up, make sure you call me over. Once you get that, basically what you're going to do is you're going to take the 100-gram weight and you're just going to hook it onto the bottom, and you're going to start to spin this thing around and try to keep that tape in place. And then you're going to put 150 grams on there and spin that sucker around and try to keep it in place and put it at different radii. And we're going to count 10 revolutions, and somebody's going to be timing it. We're all going to 1, 2, 3, 9, 10, stop the timer. That way we get a good average. All right. So on the back side, let's take a look. We're trying to figure out the angular speed and revolutions per second, so that way we can compare it up to the front. Remember how the front was 1.04? So we're hoping for about 1.04. So we're going to actually physically do this. We're going to let this thing spin around 10 times. 10 good revolutions. Somebody's going to time it. And let's say that after it's spun around 10 times, the actual time was, let's make it 11 seconds. Okay? Just make it 11 seconds just to show you how we're doing this thing. Angular speed is how many times it spins per unit time. How fast is it spinning per unit time? It's doing 10 revolutions in 11 seconds. So you can figure out your revolutions per second. 10 divided by 11 is 0.91 revolutions per second. So this is what it actually did. And this is what I thought it should do. Let's go find some percent error. All done. So really the experimental side's really easy. Counting up to 10 revolutions, somebody's timing it. Divide the 10 by the time. Divide the 10 by the time, because it's always 10 revolutions. Divide by your time. And then you can compare up later on when you get your other calculations. But before you leave, we need 2, 4, 6, 8 different spinaroonies to figure it out. Yes, sir? That's your all. So again, this was my experimental. When I spun this thing around, woo, it took 11 seconds to do 10 revolutions. So 10 revolutions divided by 11 seconds is 0.91. And then earlier, when we did the original, all those calculations, theoretically, I got that. So now I'll compare those two up and see how it goes. Yep. make sure you're comparing the revolutions per second, not the radians. Yeah. All right. Questions there? And then we got some, obviously, the questions to answer as we go along.